Let's consider the following definition. So let's let V and W both be vector spaces. Let's let T be a linear transformation from vector space V to vector space W. We are going to define the image of T, the image of the transformation. We denote it mathematically by IM, and then in parentheses the transformation. So IM of T, the image of T. And the image of T is if we take every vector in the domain and then apply the transformation to it, the set of all those transformations is the image. Okay? So in other words, the image of the transformation consists of all individual images of all vectors in V. All right? So let's say this is the domain. Okay? The domain is vector space V, and we have another vector space over here, vector space W. Now, what transformation T does is it maps everything in vector space V into vector space W. Okay, so everything in vector space V goes into vector space W, but that doesn't mean it has to fill up W. It only needs to fill up some smaller section of W. So maybe something like this. Okay, so maybe everything in V actually just goes in this little portion of vector space W. Okay, now here we're thinking abstractly. Obviously, vector space V, vector space W, we wouldn't usually visualize them as, circles or ellipses or whatever. But hopefully you get the idea. It's just vector space V, you could think of it as just a collection of stuff. So this is just, hey, all the stuff in V. This is all the stuff in W. When we apply transformation T to everything in vector space V, it doesn't need to go to fill up W. It only needs to go to a portion of it. It just needs to be in there somewhere. The portion that vector space V fills is the image of T. So in this drawing, that'd be just that section, right? That's where everything in vector space V, when we apply the transformation, it all goes into this small section here, okay? That place is called the image of T. And you probably have learned to call it a different name in algebra class. Often we'll call it the range of the function. The same idea here. It's the set just where the vector space is mapped into within W. Doesn't count all the little points over here that nothing gets into. Okay, that nothing maps to. All right. Let me give you a simple example just so you could get a feel for this. Let T go from, let's be concrete here. Let's say R3 into R5. And let's let this transformation be defined by T of any vector x that we plug in is just the zero vector. Now, the transformation that maps everything to the zero vector is a linear transformation. Okay, so the domain here is R3. The codomain is R5, five-dimensional vector space. But the image of T in this particular case consists of just one single vector, the zero vector. Not all of R5, because no matter what I plug in, only the zero vector is spit out. So that's the only thing in the image. The image is just the set of all vectors that you could actually reach from R3 by applying transformation T. Okay? So what I want to do now is think about this in particular in the sense of a matrix transformation. remember, we're thinking of linear transformations as a kind of an extension of matrices. So I want to see what happens in the special case of a matrix. What would the image of T be in the special case where it's a matrix transformation? So let's let T from Rn to Rm be a matrix transformation with standard matrix M sub T, and we'll just focus on the columns of this matrix. So column 1, column 2, all the way, there's going to be n columns to column n. Okay, now the image of T, the image of transformation T, is just everything we could possibly get by plugging something into the transformation of T. Okay? So let's take, to get an idea of the image, let's take transformation T, let's plug in an arbitrary vector, let's see what happens. So let's plug in an arbitrary vector. This would be an n-dimensional vector. Now, because M sub T is the standard matrix of transformation T, applying the transformation is the same as multiplying by the matrix, right? So I'm just going to plug the matrix in here. Okay, and if I actually do the matrix vector multiplication, I will get a linear combination of the columns of the standard matrix. So x1 times the first column plus x2 times the second column, and so on. Okay, now this is going to be true no matter what vector x I plug in. I will just get a linear combination of the columns of the matrix, right? And because I could plug in any vector x, right? Every single vector x, n-dimensional vector x that's in Rn, that's what I'm allowed to plug in, I'm going to get every possible linear combination, right? So the possible outputs, so the image of T, which is all the possible results I could get, the outputs I could get from applying transformation T, the image of T is the set of all linear combinations of the columns of the standard matrix of transformation T. Okay? But we have a special name for that. What do we call the set of all linear combinations of the columns of a matrix? That's the column space. That is, the image of T is just the column space of the standard matrix of T. Okay? They mean exactly the same thing in this particular case, right? The image of T is going to be a generalization of the column space of the matrix because we can think about what the image of T is even when a transformation doesn't have a standard matrix. When it does, the image of the transformation and the column space of the standard matrix of the transformation are equal. But if the transformation doesn't have a standard matrix, we could still think about the image of the transformation. For example, let's let T be a linear transformation from V to W. Then the image of T is a subspace of the codomain W. Okay, just like how the column space is also a subspace. All right, so this is a generalization of the observation that the column space is a subspace. Proof is straightforward. Okay, suppose we have two vectors in the image of T. In order to be in the image of T, that means there must be some vector V that when we apply T to it, and go into W, it gets us to that vector. So then there exists a V1 and V2 in the domain V such that the transformation on V1 is equal to vector W1 and the transformation on vector V2 is equal to vector W2. That's just by definition what it means to be in the image. Okay, I can get to those vectors by applying the transformation to something within the domain. Okay. Let's let A and B be scalars. Then what we need to show in order to show it's a subspace is that every scalar multiple of a vector that's in the subspace is still in the subspace, and every sum of vectors that are both in the subspace is still in the subspace, right? We need to show closure under vector addition and closure under scalar multiplication. We've seen, though, that this is going to be equivalent to just showing every linear combination of two vectors that are in the subspace is still in the subspace. So I'm going to kind of do both of these things at once by making sure that this is true, by making sure if I take a linear combination of two vectors that are in the image of T, that linear combination is also in the image of T. That would prove that the image of T is a subspace. Okay? So I'm going to take my linear combination, AW1 plus BW2, and I'm going to use what I know, right? I know that W1 and W2, because they're in the image of T, I can write W1 as T of V1 and W2 is T of V2. So I get A T of V1 plus B T of V2. Okay, but T is a linear transformation, right? Which means it preserves linear combinations. So I can move the scalars inside the transformation. I could also move the sum inside the transformation. So this is going to be equal to the transformation of A times V1 plus B times V2. And I'm done. Because I found that the transformation of some vector in V is equal to this vector here. Okay? A linear combination of W1 and W2. I know, by the way, that this is in V because V is a linear, a vector space. And vector spaces are closed under scalar multiplication and closed under vector addition. So this is exactly what it means to be in the image of T. Thus, AW1 plus BW2 is in the image of T because I can take the transformation of something in the domain and get this. And that's what it means to be in the image. So thus, this linear combination is the image of T, meaning the image of T is a vector space. Actually, let me be just a little careful here. It's a vector subspace. Okay. Remember, every vector subspace is a vector space, but I want to be clear here. Okay. So just like how the kernel or the column space of a matrix is a subspace, a vector subspace, the image of a linear transformation is a subspace. Okay. And just one more idea relating this linear transformation, this idea of the image of a transformation, to the column space of a matrix. Recall that the dimension of the column space of a matrix is equal to the rank of the matrix. Right? We showed that. Well, we are going to extend that definition to work with transformations. The rank of a linear transformation, T, is going to be the dimension of the image of T. So we are going to define that the rank of a transformation is the dimension of the image. Okay? Now, if transformation T is a matrix transformation, then these two definitions are equivalent. Okay? In the special case where the transformation is a matrix transformation, then the image of T is the same as the column space of the standard matrix of T. So the dimension of the image of T would be the dimension of the column space of the standard matrix of T. Okay? So in the special case where T is a matrix transformation, the rank of the transformation and the rank of the standard matrix of the transformation are going to be the same. But if T is not a matrix transformation, this wouldn't apply. We still have a way to define what it means to have the rank of a linear transformation, even if it's not a matrix transformation. We define it to be the dimension of the image of the transformation.